So welcome everybody. Great to have you all here today. This is the first of our seminar series, so thank you for coming along. My name is Julie Urquhart. I'm one of the ambassadors for the Future of UK Treescapes programme. And I'll be chairing this this session today from Matt. As I said, it's the first seminar that we have in our series, and these sessions are aimed at policymakers and stakeholders to help you to get some early insights into the work that's been undertaken by the Treescapes projects. There's lots going on in this space within the programme and also in other areas as well. So hopefully it will help to link up some of the activity that's going on and identify synergies with work being undertaken in other places. Could I ask everybody please to be on mute so that we don't get any interruptions. You can have your cameras off if you wish, or you can have your cameras on, that's fine. So if anything you hear in the seminar is particularly interesting for your organisation, please feel free to contact Matt and his team. They'll be able to provide you with more information, and you might be able to give them some input into how what they're doing might be useful to you. So yeah, just some housekeeping. There will be an opportunity to ask questions at the end, so we'll ask that you hold off questions until then, but please do put anything in the chat if you want to as we go along, and we'll feed that through to Matt. So yeah, so just really, I don't want to take up any more time. I'll introduce Matt. So Matt Dennis, who's the lead of the Caster project. So this is one of our projects that's looking at riparian woodland expansion. And Matt's going to be talking about some of the methods that they're using in this project. And his presentation is titled Capturing Connectivity in River Corridors. So over to you, Matt.
Thank you, Julie. Yeah, and good to see everyone. A lot of people have attended. That's really encouraging to see.
Their arms around each other saying, well done. Adil Rashid bowls so well.
Someone congratulating me already. What was that? And it's nice. The first time I've seen someone looking at a microscope on Zoom as well. That's exciting. I feel like I'm really amongst scientists today, so this is good. So yeah, I'm the PI of the Caster project, which is one of the Future of UK Treescapes projects from the first round, and we're focusing on riparian woodland. I don't want to say too much about the overall project because I do that a lot, and I've done it a couple of times this week already. So I'm just going to say we are focusing on riparian woodland, and we are a very interdisciplinary project. But the stuff I'm going to talk about today is only from one of those work packages. It's a very sort of specific little bit of work we're doing, looking at connectivity. And I think the title of the seminar is Capturing Connectivity in Riparian Corridors or something. But really, it's just starting to work through those ideas. So what I'll be presenting is less sort of mind-blowing findings, and you should do this because this is what's going on in riparian corridors, and quite a few methodological kind of considerations, really, which some of us think are really interesting and perhaps can't move on from because we're too interested in them. And others might seem less sort of relevant, but hopefully there's a mixture of sort of, some results, some nice maps, and some sort of ideas that might be interesting to people. So I think I should just start screen sharing, right, Julie?
Yeah, that'd be great. Thanks.
Here we go. Right then, so there's the lovely advert that's been put out. So thank you for my first slide, ambassadors. It's always tricky to know what to put on the first slide of these things, but thanks for putting out this lovely image, which I've found on Twitter. So just to give a quick sort of background really to what this bit of the work's about. Work package 6 is focusing on river corridors, woodland in river corridors, riparian woodland, whatever you want to call it, and how this influences connectivity, really. We think it does, don't we? We talk about river corridors. We know that corridors are things that people and animals move through to get to other places. And so obviously, when we were building the proposal for the project, it was, these are important corridors, movement corridors for nature recovery, and rivers and streams provide a sort of a network for that nature recovery. So there's a nice sort of concept and sort of blueprint behind that, which is quite tantalizing, right? It seems like it should work. We want it to work, but we also want to do a good job of knowing when it works, when it doesn't, and why, so we can make some general sort of suggestions around that. So just a few sort of bit of background to the general approach and some assumptions. That's important to get the assumptions out of the way. So hopefully there are a few questions later on about that. We're working in 3 catchments. So we're working in 2 in Cumbria, so in Ennerdale, working in partnership with Wild Ennerdale and Gareth up at Forestry England up there. In the Lowther catchment, sort of just to the northeast of there, and in the Colne Valley, which is in West Yorkshire, which people probably never heard of. But it's another large catchment in the South Pennines. For this particular bit of work, not the whole project, but for work package 6 thus far, where we've settled on around considering patches of 1 hectare or higher for looking at connectivity. So when you do these sorts of analyses, you generally take a patch-based approach, sort of a meta-population ecology style approach, where you consider patches of biodiversity supporting habitat in a wider hostile sort of environment. And we've considered patches of 1 hectare or bigger to be big enough. If we don't do that, if we insist that they're bigger than that, we soon run out of data because there aren't enough trees really to be working on. Any lower than that, and we start to worry that this is not really sort of viable habitat to be considering. What else to say? We're using a cost-based approach to looking at connectivity and assuming costs, the cost of moving to the landscape for what we call a focal generic species. And this is something that's been used by other authors and by colleagues in the Woodland Trust and Forest Research to sort of think of a hypothetical species that's dependent, a forest specialist that's dependent on good quality intact woodland to persist, and assigning various costs for that hypothetical species for moving to the landscape. We can change that later on, but we're using this because we think we're in good company, because it's what the Woodland Trust and Forest Research have used in the past as well for exploring these ideas around connectivity. Probably important to mention that we are looking at what we call functional connectivity rather than structural connectivity. So when we do functional connectivity, we're interested in movement of a particular species through the landscape, and different species have different dispersal distances, and that's important when you're looking at doing these models of connectivity. And so another assumption is that we're using dispersal distances of 1, 5, and 10 kilometers to explore these sort of hypothetical scenarios around woodland connectivity. We're doing 3 things really to try and start to look at what these riparian corridors do, what they sort of can contribute. One of them is just to assume we can green up riparian corridors, that where there aren't currently trees, in a perfect world, notwithstanding sort of, infrastructure and things like that, but hypothetically speaking, we can green these corridors and then see what impact that has in terms of reducing cost of movement in the landscape and increasing connectivity. The second thing we're trying to do is just to add in new patches, so patches of different sizes starting from 2 hectare, 5, 10 hectare, adding them into places that intersect this riparian corridor, so that's sort of involved with this riparian area, and also adding in similar patches to the wider landscape, so in the catchment. We're only using one real constraint, is that we are only considering what comes under grassland, the various sort of types of grassland in the UK land cover map. So we're excluding more problematic things like areas of bog and sort of complicated urban areas and things like this. And in terms of what riparian means, we're still debating that, believe it or not, after a year or more. But there are a couple of definitions out there. So we've used the Environment Agency definition of river buffer width, which is a function of the width of the stream or the river itself. So we're using that sort of kind of a bog standard approach rather than something that's it's not quite fixed width, but it's not super variable either. It's not a floodplain model. So it's using something that's roughly in the middle and has some sort of traction in terms of practice. Other thing to say is that in terms of measuring probability, there are different ways you can do it. I've mentioned already that we're looking at functional connectivity, and there are various metrics you can then use to do functional connectivity well. And where we've been using what we call the probability of connectivity metric to assess changes in connectivity. And just to explain that briefly, so this metric takes the probability that different patches are connected to each other based on the cost of moving through the intervening landscape. It then takes the product of all these probabilities for all patches and the product of all patch areas, adds that all together and divides it by the study area. So there's a bit of maths involved, but it's basically all the probabilities, all the patch sizes, multiply them all together, and then you divide by something suitable, which in this case is the study area, and you get this probability of connectivity for that study area. So that's enough on the background and the assumptions. So just a little bit of background on some theory, maybe, and there are two general approaches that we've considered when it comes to measuring connectivity. These are resistance-based metrics on the one hand, and functional connectivity metrics on the other hand. Resistance-based metrics come from ideas around circuit theory, and these are less easy to integrate into, I think, into functional connectivity metrics. So typically for doing functional connectivity, we use a least cost approach, which is first of all, it's thought to be better than just doing a simple sort of Euclidean distance measure of distance between patches. And it considers the relative cost of moving through various features and land covers habitats in the landscape. Circuit theory sort of came around a few years ago, claims to do a better job than a least cost approach, citing that least cost approaches assume that an organism has complete knowledge of its surroundings and therefore always chooses the least cost path. It always chooses the best option, which seems unrealistic. And circuit-based approaches, in a sense, they do the opposite and assume what we call a complete random walk. And what this means is that there are more possible routes with circuit theory to get from one point to another for an organism and to travel between different patches. In some ways, this is more realistic, but it can be challenging to incorporate the results from this into measures of functional connectivity. And this is because I mentioned earlier that functional connectivity, a key thing is knowing the dispersal distance or the dispersal capacity of the particular species that you're working with. We can do this using cost-based approaches because we can easily translate cost of moving through a 10-meter cell to the actual distance in the landscape. So it's easier to equate the two. It's harder with circuit theory because, for one thing, there are multiple paths, and that tends to reduce the overall sort of resistance in the landscape. And also the results that you get aren't in sort of distance units. They're in something called ohms because it's linked to sort of electrical circuits. And it's challenging to equate the results you get in ohms, let's say, to meters or to kilometers. There are a bunch of suggestions on how to do this. So some people say, well, you just take all the costs in the landscape and all the results from circuit theory, and you regress one against the other, or you divide one by the other, or something like this, which seems reasonable. But I think some of us are skeptical that why go to the effort of creating something new and better if you're going to make even more effort to try and equate it to the old thing that you were using. So I'm not entirely convinced about that. But in the end, they're two very good approaches, and we're sort of using both and trying to use the best bits of each one really to capture different types of connectivity. So just a little sort of methodological aside there before I get into the actual sort of details of the study itself. Okay, so I mentioned that the two are sort of linked, but can give you different results. And what we found was that if we use least cost path and circuit theory, you get similar trends, but the values can be quite different. So here we've used a metric ECA on the left-hand side on the y-axis there. This stands for equivalent connected area, and it's something that you can derive from the probability of connectivity. And we found that if you try and equate the results in ohms that you get from circuit theory to actual distances in space, and then run the same models, you get a very similar trend. But with the circuit theory approach, or the Circuitscapes application that we've used, it overestimates, we think, the equivalent connected area. And that's because with many more possibilities in the landscape using a random walk, it tends to bring down the overall resistance. And due to difficulties in converting that to dispersal distances, as I mentioned, it's difficult to come up with scenarios that seem reasonable and that aren't sort of highly sort of optimistic versus a least cost path approach. You can play around with that, so you can sort of try and experiment with dispersal values, not distances, but values that then bring your circuitscape results into some sort of range that's similar to the least cost path approach. But then again, I think, well, why bother? Why bother using two different approaches if you're going to go to lengths to then try and sort of bring the two closer together? You may as well just, use one or neither. So I think that the best approach is to use both sort of in tandem and use the best bits of the results, if you like, to look at different aspects of connectivity. So just a little bit of context there on these two approaches. We've also explored some patch relationships. So I mentioned that these metrics, so probability of connectivity, this PC metric, it's a function of the probability of two patches being connected and the size of those patches as well. Now, there's a whole sort of conversation around the importance of patch size here that could be had, and hopefully we can have that sort of later on, because I will touch on it in a bit as well. But one of the reasons that we include patch size is because it's a sort of a quality for area, the number of resources, the amount of core habitat that you've got in a patch of woodland, and it sort of seems to make sense. There are calls to try and do a bit of a better job of that. So one way is to consider edge effects, and we've not done that for another reason, which I'll get onto later. And another option is to use things like LiDAR to consider the structural complexity of patches, assuming that the structural complexity is more diverse, probably got more sort of age bands in the woodland, and basically of a better quality. And so we've used LiDAR data to calculate something called the vertical complexity index. That's what the VCI stands for here on this plot on the left. And there's a decent agreement between patch area and vertical complexity. Based on that, based on some sort of work in one of the catchments, we've continued to use area as a surrogate for quality, with some testing to sort of justify that. So mapping these connectivity routes and thinking about patch contribution to connectivity. So these are the results that come out of the Circuitscape, the circuit theory results. Now, notwithstanding those sort of methodological kind of problems that I mentioned earlier, they do produce nice visual and intuitive and helpful maps to help you look at, where there is more connectivity in the landscape. So on the left here, well, in both images, the brighter colors are telling us where there's more connectivity, there's more sort of ease of movement through the landscape. And they tend to turn up where you've got more patches of woodland and least cost between them. So they map quite nicely onto where the trees are. They also map quite nicely onto where the rivers are. And what we've found is that for all three catchments, between about 80 and 95% of all the woodland intersects the riparian zone as defined by the Environment Agency. So one of the first things that we sort of realized was that, well, we're putting a lot of emphasis on riparian woodland and let's have more riparian woodland. But it turns out that these riparian zones seem to be acting as a kind of refugia in the first place. A lot of our large intact woodland is actually connecting with near this riparian zone. So what that means is that already a lot of our river networks are intersecting with these areas of high connectivity. And in particular, the slightly larger rivers, so not quite the headwaters where we don't tend to have trees in our upland areas, but in the slightly sort of more lower down areas where we've got rivers over a metre or two, then we get pretty much double the background current in terms of ease of movement based on the costs that we've used in our assessment. So you might say, well, that's job done, we know they're important, but I still think it's key to look at different scenarios and think about, what happens when you do make these rivers green, or when you do put more trees near them or at a distance. We've been thinking about sort of the scale of the analysis as well. So, I mean, there's a bunch of geographers on the project, so we have to think about scale and things like this. And there's another geography problem that I'll come on to in a bit. And yeah, so I think the scale of the analysis that we adopt, as many of us know that work in this sort of field, is important and it can affect our results. So we're working with these focal catchments that I mentioned, so Ennerdale, the Colne Valley and the Lowther catchment. But we want to consider the woodland around these as well. We wouldn't be doing a good job if we just considered what's going on in these catchments and didn't consider the connectivity, the links around them, the sort of the cost and the various patches that exist around these different catchments. And catchments tend to be irregularly shaped, right? They don't tend to be so neat and tidy for our analysis. And what seems to be happening is that you do get slightly different results depending on the scale that you perform your connectivity work, let's say. So on this map on the left, you've got each patch is represented by a little bubble there, and the larger patches tell you the contribution of that patch to overall connectivity in that catchment, and that includes all the bits inside the sort of black line there. So you can say, okay, fine, we're working in this catchment. This is the importance of the woodland, so we should value these more. But if you take a slightly wider view and include things in the surrounding catchments, then the size of these bubbles and the distribution of these sizes, it can flip quite dramatically. And suddenly, at that sort of level of perception, the things that you thought were important or contributing a lot suddenly don't really matter. We just need to concentrate on this over here. So I'm not saying that's the case, but just to highlight that we need to think about various scenarios, and we need to have versions of these analyses, certainly, for maybe different stakeholders, different sort of decision makers, and for different species. So all these things are going to interact and hopefully determine in a sensible way the scale at which we're going to carry out these analyses going forward. It's important to think about scale because, there might be trade-offs, maybe different processes work at different scales. So we're also looking at potential for flood alleviation and how water behaves as a function of vegetation and trees in the landscape as well. So we need to think about the scale that our colleagues doing that work are working at, and if and where there might come up against the trade-offs in terms of, we think this scale is important, and they're saying, this is all that matters here. So can you sort of please do something that makes sense to us as well? So we need to know about these potential trade-offs, both in terms of maybe ecosystem services, but also just analytically speaking, at what scale we do these sort of analyses. Working with sort of hydrology and geomorphology might have a characteristic sort of scale for the processes or the types of data they use. And are we sort of able to speak to that based on the decisions that we're making in the more sort of GIS and spatial work that we're doing? Another thing that I think is worth mentioning is that we wanted to consider each catchment and the catchments around our focal catchment. And I think there was probably an assumption that they would have some special quality to them because they're in the middle, because they're these catchments. All the trees in this catchment will affect the ones outside it because we've decided to work there and they're special. But it doesn't necessarily happen, and it seems to be much more a function of, we think, topography, the configuration and size of the actual treescape that's there already. And there's not necessarily anything special about sort of focusing on the middle catchment in any scenario. And what is the middle catchment anyway? So I just thought I'd put that in there as a sort of a reminder that was a bit of a silly idea, perhaps. Okay, so just a little bit of focus on what I mean by sort of how we can green these corridors, how we can model that in practice. So it's fairly simple, actually. We can get the river network. We can get that from openly available data. We can arbitrarily sort of burn that into the catchment, if you like. So that's step 2 here. We can overlay where the rivers are and where the river buffers are according to the Environment Agency, and say, right, well, we'll overlay that and say, right, we can all these pixels, all these sort of this network in the landscape, we can turn these into trees. Probably highly unrealistic, given there'll be bits of infrastructure and barriers to that. But we're operating in a hypothetical sort of sense. We can sort of try that out. And then we do some new cost calculations. So I mentioned before this sort of probability of moving through and connecting to patches, all based on the cost of a particular species moving to the landscape. So we can put essentially more trees along the rivers using this method and then recalculate cost. And the assumption is that, well, mathematically that cost should come down. So we should see some sort of improvement. We do see increases in connectivity, but it varies between catchments, basically. So some catchments have a big increase in the probability of connectivity for that particular place, and some catchments don't. So this is work I'm just showing on this screen that's based on all the sub-catchments in all the study areas so far. So that equals about 40 sub-catchments, something like that. And overall, it seems that catchment size makes a difference. And I'll get onto sort of the problem of thinking about size and study areas and extent later. But it seems to be easier, or at least it seems to have a bigger effect when you stick a green riparian corridor in a smaller catchment. There's just, more new pixels per unit area. So that sort of seems to make sense. And there's an overall trend where, the amount of existing woodland that's there gives you more sort of increased connectivity. So if you green a corridor that's already got patches that are joined to it, you get a bigger increase in connectivity. Also makes sense. When we look at changes in individual catchments only, so this is not aggregating the whole sort of data set, if you like, it's looking at Lowther, then looking at Colne, then looking at Ennerdale. You don't get this as anywhere near as clear a picture as that. So in some catchments, it seems to be that the catchment woodland, sort of generally the canopy cover in the catchment is what matters. In Ennerdale, it seemed to be really sort of more focused around how much riparian woodland was already there. And in the Lowther catchment, none of that seemed to matter. It was just how close together patches are. So there's a lot to unpick in all of this. And I just do this to highlight that, again, the different scales that we work at, the different units of analysis can tell us different things. And one of the reasons why we're sort of trudging through a lot of this process is to try and pick out what's really happening, what's really a pattern with a process behind it, and what's kind of an artifact of the scale that you're working at. So this is something we always need to kind of keep in mind. So to talk a bit more about the influence of scale on the patch level now, I've got a bit of a worked example which hopefully will explain some of the things that we're thinking through on the project at the minute. So it's important to say something about the relevance of patch size, I think, in these assessments. So here's a very basic example of two landscapes with the same total area. On the left, this sort of PC metric that we can calculate is 0.3, which is basically the result of 0.5 squared times 10 squared and divided by the whole study area, which in this case is 100 hectares. So we divide that product, if you like, or the sum of those products by 100 hectare squared, and we get 0.03. And then on the right-hand side here, we've got the same amount of total cover, but because we've got more patches, then what tends to happen is we have to multiply these connectivities, these probabilities more times, right? So there are more patches. We need to multiply 0.5 by itself more times. What that has the impact of bringing down this overall sort of PC metric. So what we're finding is, as we look in more detail into these various metrics that we can use, is that there seems to be a bias towards really having fewer larger patches, because the fewer patches you have, the fewer times you've got to multiply everything by something less than one, right? So that means that it's better to have bigger and obviously more joined up patches. I think this is okay, and I think a lot of us that are sort of still hearing the echoes of the Lawton report, and now everything that comes out is basically a iteration of bigger, better, more joined up, and that's where we're starting from, I think, a lot of the time. That makes sense to us. We should have fewer, bigger ones. also backed up by some work coming out from the tropics about land sparing versus sharing and agriculture, that kind of thing. But it's something to be aware of. And there are recent papers coming out on the SLOS debate, for example, Farid's paper last year that actually demonstrated the opposite, that having fewer, more numerous patches will give you higher species richness. And that was based on a very large review, and it's that paper's carrying a lot of weight currently. So are we going to find similar things in our catchment? If we do, is it a function of just the way the metrics are set up? So this is something we're thinking about, if there are ways we can sort of conceive something slightly new that will help us to downweight this influence of bigger patches always inherently being better in the way these metrics are set up. I've then got another problem for you. So I think something called the modifiable aerial unit problem also comes into this. And this is a problem in geography where when you're working with spatial data, the way in which your data is grouped, divided, sort of sliced up in space can affect the results you get when you're running your analyses. So think of a typical kind of regression analyses. You might use something that's typically kind of not even and challenging to work with are data that come from the census. So low super output areas, things like this. Very irregular in terms of shape and size, but we're forced to use them because that's the way the census is reported and things like this. And they're arbitrary, they're based on roughly population and some features in the landscape, but they're not something that's been decided by analysts that would be best for them. And they determine the way your data's sort of sliced up, if you like, and that can alter your results. So I've tried to sort of exemplify this here as well. So here's another hypothetical example then, where we've increased the number of patches again by 1, but I've kept the probabilities of movement the same. You might think that's unlikely, but I'm assuming a very heterogeneous landscape in which the probability more or less works out to be the same between patches. We've just got one more patch. We can see that the PC metric goes down again slightly with this 100-hectare study area. But if we happen to be working in catchments, which we are, then what if the catchment we're working in happened to be 50 hectares rather than 100? So let's say the study area is more like this. And that can happen because we don't decide the shape or the size of catchments, right? So what we're seeing is in some of our study areas in the Colne Valley, the catchments tend to be smaller than up in the Lake District, and that's just a function of the history and climate and geomorphology and all this kind of stuff. There's not much we can do about it. So we might have a situation where this configuration is in a 100-hectare catchment or one that's half the size, And because of that, if we then divide the results of these probabilities in area and stuff by 50 hectares squared instead of 100, then we get a much higher metric now for our probability. So again, this is something we need to be aware of when we're making assumptions and drawing conclusions from our analyses. There's a way around this, and so people suggested that, well, instead of dividing by the whole study area, so 100 hectare or 50 hectare, just divide by the amount of habitat, because that's a more reliable thing that doesn't move around as much, and it's the thing that we're interested in anyway, right? So maybe just use the habitat area. If you do that, that sort of maybe seems to fix the problem, and you get a PC number now of 0.6. But there's a problem with that, and we came up against this problem because we are actively trying to model putting more trees in the landscape. So what happens with that, if you only divide by habitat area, it's pretty much impossible to get your PC metric to go up, because every time you're adding in a patch, yes, the area goes up, but also the probability has to be factored in. And unless that probability is 1, so in other words, unless you're adding to an existing patch, any new patch added to the landscape tends to bring your probability of connectivity down. So again, this is something we hit up against slightly, which is very interesting, and we're spending time on working through, but something that we're hoping to modify slightly and come up with something that does a slightly more honest job of allowing woodland to be added to the landscape using this sort of metric, but that doesn't sort of degrade your overall sort of metric that you come up with. So we think that these metrics are potentially favour bigger areas. And what we're seeing is that when you add in patches to the landscape, so this is adding in randomly into grassland in our catchments, patches of 2 hectare or 10 hectare. When you add in 10 hectares for the same overall area increase, you tend to get a more bang for your buck, if you like. You tend to get more increase in this probability of connectivity. Question is, and you're all wondering now, is that because that's what's happening, or because these metrics are biased towards bigger patches? And that's what's sort of keeping me awake at night currently. Just a quick note on what happens when you do sort of catchment versus riparian. Well, I have to say, for 2 of our catchments, so looking at Ennerdale, looking at Lowther, there's no difference. It doesn't matter where you put them, just put them in the landscape and this PC metric goes up. The only case where it seems to favour riparian is in the Colne Valley. Why we think that is just because of some basic differences in the characteristics of these catchments. So some are bigger than others. Colne Valley has smaller catchments. It's been developed over time in different ways. The catchments are just smaller. That's how it is. It has a huge area of bog, which we excluded from the analyses. So we think that a lot of the new patches that we're sort of allowed to add within the constraints of the model tends to cluster them near rivers, basically. We're not quite sure yet, but we do see some differences between catchments. And if we can put our finger on what causes those differences, then we think we're starting to get into something quite interesting in this project. Finally, I mean, when we're working with these sorts of methods, it's almost always better just to increase the size of existing patches. So we go through all these efforts to do functional connectivity over structural, to consider circuit theory and other least cost methods, to put riparian and put catchment in. But if we have put our faith in the sort of the usefulness of this overall PC metric that we're using, then it's almost always better just to make existing patches bigger, because you don't decrease the probability of connection between any of them, but you increase the amount of area that you're adding into this calculation, right? So again, this speaks to what we think we know about, bigger, better joined up. And often we talk about new woodland, planting it and what have you, and we neglect to think about protecting existing woodland and doing a better job of managing what we already have. And there's a lot of sense in that. And this sort of result, again, it would support that kind of approach. And yet we still need to be sure that we're not sort of overdoing it by biasing things towards larger patches and just in the numbers. Okay, so just to summarize really, and I've been keen to not conclude, because a lot of this is methods and questions that we're working through on the project. But yes, so the scale of analysis clearly matters, and that can be a problem and an opportunity. It's a problem because, working on the maths and trying to draw conclusions and test hypotheses and those sort of scientific things, it can get in the way. But actually, it means we're also quite flexible. We can work at different scales. We can consider a problem for a species, or for a catchment, or for one region where there's a new sort of initiative. That's something. Let's take the Northern Forest, for example. We can apply these things to scale, and through sensitivity analyses and things, hopefully come up with something that fits for that scale of work. It's important to consider whether these sort of considerations around scale are to do with something that's happening in the real world, or just something that we've forgotten about and turns up inside the techniques that we're using as an artifact in our results. That's also very important, and something that I think, as academics, we need to be working on and driving. Sorry, but we can't ignore the geography. I know this is largely a landscape ecology sort of endeavour, but there are some very important geographical problems that we're proud of that you all need to think about and consider. And one of them is the modified aerial unit problem. And it's something that actually I didn't realise would be a problem until recently. And it's all about the fact that we're working with catchments, which are these arbitrary sort of units. So yeah, to conclude with the question, really, do we need new metrics is strong, maybe adjustments to existing metrics that are somehow moving us towards a scaling variance, and consider boundary effects. So I noticed, I mentioned earlier that considering a wider study area reduces artificially what seemed to be important in the landscape? And can we come up with something that sort of takes that into account, working at different scales? So yeah, that's kind of the inside of my mind of the past year. And I can stop there for questions, Julie, if that's okay.
Yeah, that sounds perfect. Thanks very much, Matt. That was great. Do you want, yeah, you've stopped sharing. Perfect. Yeah, so open the floor up for questions for Matt. There is one in the chat, yeah, from Justin. Could the area of analysis be some kind of buffer around the study's habitats as a function of the dispersal distance that you're looking at?
Yeah, well, exactly. So I'm not a huge fan of buffers because they're also quite arbitrary, but you've got to stop somewhere, right? So you've got to think, okay, how big is big enough? And that's why we thought, well, we need to consider all of our catchments, but we need to consider the ones around it so that we can think about, you know, wider connectivity. What does connectivity of our focal catchment contribute to, you know, catchments outside of it? That's proved to be quite inconclusive, and it might be to do with, you know, we've used this generic focal species, which seems like a contradiction in terms, doesn't it, in a sense, but we've used this sort of generic species with costs attached to it. And these results will be very different and require different size study areas if focusing on different species. Problem is, there's potentially no end to that, and the results could become intractable. So where we're at with a lot of this is doing something that is complex and honest enough and has enough results, enough versions to, you know, have a sensitivity sort of approach and be able to draw conclusions, but it's not so complex that it's actually impossible to transfer in a logical way to the real world. It becomes intractable once so many permutations become involved. And I think that's kind of the problem that we're always hitting up against in sort of fields like geography and ecology. The world's complex. To what degree do we need to reduce it to understand it? And it's, I don't think anyone's got the answer to that yet. Yeah. But yeah, very good question. Thank you.
Great, thanks. We've got another question from Louise from Defra, who is asking if you could say something about the shape of the different patches and do they affect connectivity, and have you included that in the analysis?
Yes and no. So there's one way in which we categorically fail at doing that, and that is because at least for some of the metrics, for the least cost approach, you use the patch centroid, which is not ideal. You want to be using the patch edge maybe. Circuit theory sort of gets around that because you can collapse patches into one focal point with zero resistance sort of thing. So that sort of helps you to get around that. But in terms of the shape, no. And I mentioned at the start that we'd consider looking at edge effects because I think this is important. And I think accounting for the influence of surrounding, you know, land uses on biodiversity supporting habitat, we need to factor that in. And it's something that also helps us to get around these area biased problems, I think, because you can, you know, you're reducing the core area depending on the context that you put in a new patch of woodland, let's say. And when we employed some of the available approaches to accounting for things like edge effect, we found that all our riparian woodland disappeared because of the shape of it, right? Because it's along river corridors. They tend to be very long and big, but they're also narrow. So I do think we need to consider the shape of it. Thus far, we've sort of said, oh, well, we can't consider that because it just annihilates all the woodland. We've got nothing to work on. But I do hope there'll be some way of getting at these more structural components of sort of patch size and shape perimeter area ratio, this kind of thing, and maybe incorporating that into the functional stuff we're doing. That's a bit of a holy grail, I think, for landscape ecology to try and do them both at the same time. But yeah, we'll have a bash.
Right. Is that okay, Louise?
Yeah, that's really interesting. I didn't realize that it was so difficult to incorporate shape actually. So that's interesting to know.
I'll get back to you. Hopefully it's not too difficult.
Yeah, so do feel free to put your hand up if you'd like to ask a question. We've got another couple of questions in the chat, but if you want to ask a question directly to Matt, then please do. So Lindsay Muskell's asking what rules you used for location of new woodland. So, for example, abiotic conditions, habitat type, or was it just riverine buffer? She's also wondering about the connection between habitat quality, which has been included in least cost. For example, which habitats being replaced and connectivity.
Yeah, it's something we've thought about quite a lot, and it's again, it's a balance, because ideally we'd like to work in a neutral landscape where we can just turn things on and off and think about what is the result, where we can control for everything basically, and just think about distance, cost, size, shape. That would be perfect. We can do that with hypothetical models, but we can't do that with data that comes from the real world based on the catchments that we're working in. So in terms of site selection, no, it's random, and we run a random sort of series of additions of new woodland many times, and then calculate sort of mean values for how that influences connectivity. So if we try to do something that's a bit more constrained, that looked at these, say, abiotic conditions, I think that would be more useful from a practical point of view, but would be less handy for us to come across general principles that we can think, this is something this is a process that's happening in the real world, sort of thing. But yeah, ideally we do both, but currently we don't consider anything climatic or abiotic. Yeah.
Does that answer your question, Lindsay?
Yeah, thanks.
Okay, great.
You've got a question.
Stephen's got a question. Yeah. So, are you considering a temporal dimension? So, whether these treescape patches might come and go or change over time?
No, but we could. I mean, it wouldn't be too much of an extension to change the, with sort of a Monte Carlo sort of process where you're doing this many times and looking at means and distributions, to something that assumes change in time. We want to do lots of kind of simulation stuff, testing out ways in which we can maybe sidestep what we think is too much of a bias towards larger patches, or at least explore that possibility. And when we're building hypothetical landscapes towards that, this could be something that we look at as well. But yeah, connectivity tends to be pretty much exclusively spatial consideration, and I don't think anyone's looked at temporal changes yet. But I also think the connectivity kind of literature is a little bit insular, and needs to cross over a bit more to other things like the sloss debate, and temporal changes and more dynamic things that are going on in landscape. So very good point.
Yeah, really interesting.
Justin Byrne has his hand raised. He wants to unmute.
Thanks, Matt, for the talk. It was really good. I was wondering, in meta-population kind of work, we tend to consider patches to be of equal value, but when we're thinking about dispersal, it might be that species are dispersing from one site to another, especially like vegetation. We know that's a very slow process that tends to happen from well-established sites to newer sites. Have you considered maybe looking at, say, the ancient woodland inventory and looking at how dispersal patterns from those sites to new sites might be affected? So having a kind of directional flow through things and seeing if maybe where additions of woodland in areas will increase the ability of species to flow from ancient woodland sites to newer sites or areas they haven't yet reached.
I hadn't thought of that until a couple of days ago, as someone was talking about ancient woodland in a meeting that I was in, and the data sets that are available on it. And I do know there are, at least in the Colne Valley, some pockets of ancient woodland, and it's getting at that sense of quality. And we talk about quality a lot, but what do we mean? Do we mean number of resources, number of dispersers? They're basically the same. And there are new methods as well, like randomized shortest paths, that can help you with doing connectivity, but factoring in things like mortality and actual sort of dispersal success. So that's all quite exciting. And so I think once we've got past this whole, is bigger better or not, moving on to quality, can't make any promises, but it's something we'd like to sort of get in there, because it's something we've talked about for a long time. How do you do quality well? you'd like to think that size is always a kind of a surrogate, but there'll be other, you bring age into it and it changes everything, I think.
I think it's quite important because, ancient woodland sites tend to be areas that are difficult to farm, which are river valleys. So there's going to be a large overlap between the study sites that you're interested in and whether or not they're ancient woodland, or pause sites, for example. So you might find that it ends up being that your riverine network is also the network of where those ancient woodland indicators and things like that tend to live. So I think there could be a lot of overlap there, and kind of like
Thank you for that. That'll be at the start of my next talk, I reckon. Yeah, I'll look into that. Thank you very much. Obvious, but yeah, needed that reminder. Thank you.
Great, that's really helpful. Any more questions for Matt? Give you a few moments to think.
Asked, Stephen's question in the chat.
Yes, I've asked that question. Yeah. I can't see any more questions. Are you happy for people to get in touch with you, Matt, beyond outside?
Oh yeah.
Yeah. So
sure. Yeah, please. Yeah.
Matt's details are on the Treescapes website. So if you want to find out more about what the Caster's doing, and have got any further comments, you can get in touch with Matt directly. That would be great.
Yeah, anyone interested in these sorts of ideas, I'd be very happy to link up, because we'll be coming up with things that we think do a good job, and we want lots of eyes on this to see if we're doing a good job.
Yeah, brilliant. Okay, if we don't have more questions, I think we can finish here.